A single mother applies for a mortgage. She has a 742 credit score, 12 years of stable employment, and a 28% debt-to-income ratio. The application is processed and denied in 340 milliseconds. Then the AI outputs risk score insufficient. There is no human underwriter to contact and no mechanism provided to appeal the decision. In 2025, over $200 billion flowed into building AI decision engines. Less than 1% went toward governance infrastructure to control them. To fix this, we need to insert a constitutional constraint layer directly into the deployment pipeline. It takes 5 lines of Python. An engineer runs pip install acgs and imports the rule set, the constitution, into the environment. When the AI attempts an unsafe or unapproved action, the engine deterministically blocks the execution. It returns a specific denial code and a unique cryptographic hash documenting the event. A hash is a fixed-length string of characters generated by an algorithm to securely map and identify data. System prompts and statistical alignment techniques are vulnerable to jailbreaks. Reliable control requires hard-coded mathematical infrastructure at the deployment level. The European Union's AI Act takes full regulatory enforcement in August 2026. Non-compliance carries severe financial penalties, scaling up to 7% of a company's global annual revenue. The legal burden is shifting. If a system causes harm, the liability no longer rests entirely with the company that trained the foundation model. It falls on the enterprise that deployed it into production. The early web only became commercially viable for transactions once SSL and TLS, cryptographic protocols designed to secure network communications, provided verifiable security. AI requires an equivalent standard, an HTTPS for AI. Operating an AI system at scale without a mathematically provable governance layer is rapidly becoming an uninsurable risk. When large language models, or LLMs, AI systems designed to process and generate human language, require API calls that already take seconds, adding further delays for rule validation is often rejected by engineering teams. To eliminate this bottleneck, ACGS uses the Aho-Karasik algorithm. This is a string-searching algorithm that locates all occurrences of multiple keywords in a single pass over the text. It compiles a human-readable YAML constitution into a finite state machine. A live text string from the AI's output flows continuously through the trie-data structure. The moment a banned concept is matched, the specific nodes register a violation without pausing the data stream. This architecture achieves big O of n time complexity, meaning the processing time scales linearly with the length of the text. The actual validation executes in exactly 560 nanoseconds. You can add hundreds of constraints to the constitution, and that execution speed remains constant. By mathematically solving the latency problem, engineers can place deterministic safety gates directly in the critical path of high-throughput AI applications. Current autonomous agent architectures often contain a structural flaw. The same agent generating an output is given the authority to validate and approve it. To prevent this, the system relies on MACI, or Machine-to-Machine Algorithmic Constitutional Infrastructure. This framework programmatically enforces strict role boundaries. The architecture divides into 4 strict quadrants: proposer, validator, executor, and observer. In a real-world deployment, an AI proposer writes a merge request. If that proposer attempts to authorize its own code, it strikes a hard red wall. ACGS blocks the execution because the agent's assigned role lacks the explicit permission set to approve its own work. True autonomous agent deployment is structurally unsafe without this hard-coded separation of powers. Returning to the alphanumeric hash generated during that initial terminal block, the engine hashes the entire rule set. Any unauthorized alteration to a single rule changes the system's baseline mathematical state. This creates a rule snapshot history. It provides an immutable version record of the Constitution over time. Every single AI action, whether it is approved or denied, is permanently changed to the specific time-stamped version of the rules it was evaluated against. Standard application logging can be easily overwritten or altered after an AI failure. This ledger cannot be modified. If an enterprise faces a regulatory audit or a liability claim, this tamper-evident audit trail serves as the exact, unforgeable receipt of the system's decision-making process. This architecture scales beyond the European Union. It automatically maps to global compliance frameworks, fulfilling dozens of regulatory checklist items instantly. It integrates U.S. federal guidelines, specifically fulfilling the requirements of the NIST AI Risk Management Framework. NIST is the National Institute of Standards and Technology, a federal agency that develops cybersecurity and AI guidelines. It covers specialized municipal regulations, such as New York City's Local Law 144, which governs the use of automated employment decision tools in hiring. And it aligns with international economic baseline standards, like the AI principles established by the OECD. The OECD is the Organization for Economic Cooperation and Development, an intergovernmental entity that shapes global policy. The governance layer operates as a drop-in wrapper across major platforms, including OpenAI, Anthropic, LangChain, and Lite LLM. Enterprise compliance no longer requires a multi-year consulting project. It is a 5-line middleware integration. The ACGS codebase was built entirely by a creator with no technical background and no computer science degree. Every architecture decision, optimization, and test in this repository was generated through 2 years of continuous prompting with Claude, Anthropic's AI assistant. The very system designed to constrain the machines was actually built from the ground up by the machines themselves. AI governance cannot be locked behind proprietary software walls, built exclusively by a small group of elite software engineers. If a non-technical person can produce production-grade governance infrastructure, then the people most affected by these algorithms, the single mother applying for a mortgage, the candidate looking for a job, can inspect and enforce the rules governing their lives. The infrastructure to securely scale AI into high-stakes environments already exists. The only remaining step is to install it.